Hey guys, well we're going to talk about section 5.7 now, application of Newton's laws. So we're going to get down to the nitty-gritty of how you apply Newton's laws to an object. You know this pretty well, F equals ma, you find the net forces, you find acceleration by dividing the net force by the mass. If you know 2 out of the 3 things in the F equals ma formula, you can find the third. That's pretty basic. But let's kind of dig down a little deeper. Let's take a look at this bold statement here that says when we apply Newton's laws to an object, we're interested only in the external forces that act on the object. What does that mean? Well, let's take a kind of simple example. Let's suppose we're pushing 2 boxes, box A and box B, with a force external that causes both boxes to move together. When both boxes move together, we treat them as a system, and we don't worry about how much force is exerted by box A on box B and how much force is exerted by box B on box A. We treat them as a single system, and we're only concerned about what the external force is on both boxes. In the book, we have another example. We have a rock climber. We modeled the rock climber as a particle or maybe a board that is a piece of wood that has a cable attached to the middle of it and then is transmitting some compression force to the cliff face. But we're not worried about how much pressure is on the hip joint or the knee joint or the particular tendon in the knee or a particular bone in the foot. All of those internal forces we just ignore because ultimately, as long as the body is more or less moving together, we don't care about those internal forces. So we're only going to be concerned about external forces. All right. Another simplifying assumption, which we are used to, is we're going to neglect the mass of ropes, strings, or cables. We're going to treat the body as a particle. We're going to assume no friction. We make all these simplifying assumptions just to make our job easier. If we wanted to take into account the masses of the ropes and the cables, we'd have to model them using the F equals ma law, as well as modeling the motion or the forces on the particular body or particle. Okay. Well, so we're not worrying about the internal forces, we're modeling the object as particles, we're assuming no friction, ropes have no mass. When we get to pulleys, pulleys have no mass, otherwise they'd have rotational inertia, which we would get into. Okay. So we have a couple basic types of problems. We have one that are called equilibrium problems where things don't move, and in those cases we know that the sum of the forces on the system is 0, and so we just solve the problem by adding up all the forces. They should add to 0. Typically we know 2 of the forces and we're trying to find the third force. So those aren't hard problems. The problem here, the rock climber, is an equilibrium problem, because right at the moment the rock climber is not going anywhere. So the sum of the forces has to equal up to 0. Okay. And the other type of problems are the dynamic problems where the object does experience a net force and the magnitude of the net force is proportional to the acceleration. The acceleration is proportional to the force and inversely proportional to the mass. You know, when we model these dynamic problems, that the x and y directions are often separated out. In the case shown here, the movement is in the x direction because the force, that's the net force, is applied in the x direction. The forces in the y direction cancel each other out, and therefore there's no movement in the y direction. The forces in the y direction for objects resting on a surface are often the gravitational force and the normal force. Just keep in mind that the normal force does not necessarily always equal the normal force. For example, when we push down on top of a book resting on a table, the normal force is going to be greater than the force of gravity because of the applied force on top. Also note that the normal force in this book is often written as a little n rather than a big N or an F sub n. So just don't be confused by that. Okay. Classic example of an equilibrium problem is one where we have to divide vectors between x and y components. In this kind of classic example, where there are two tension forces, we can resolve these two tension forces into x and y components. The y components add up to the force of gravity. The x components cancel each other. How do we know the x components cancel each other? Because if this traffic light is not moving, by definition, the acceleration in the x direction is 0, as well as the acceleration in the y direction. And so the two forces in the x direction must add up to 0. Okay. Please do the example problems in this chapter. They're always helpful because you can see your solutions there. Typical problem of objects on a ramp. When something is on a ramp, the angle of the ramp is the same as this angle here between the x and y components of the gravitational force. Typically, the normal force pushing up from the road surface is exactly equal to the component of the gravitational force that's pushing the car into the road surface, which is mg cosine theta. The gravitational force that's pulling the car down the slope is mg sine theta. Okay, very basic problems. Here's the box problem again. Now, when both of these boxes are moving together, we can model them as a single system and only be worried about the external forces. But let's suppose some devious, diabolical, fiendish physics professor asked you to find the forces between the individual boxes. Well, then you would pay attention to the internal forces. The force exerted on each box would be the force that's required to accelerate that particular mass of that particular box at the rate which we know the boxes are accelerating. So typically in a problem like that, even if the boxes are accelerating together, you still can find the forces acting between them because the amount of force required to accelerate a particular box is always in proportion to the force and, the acceleration is always in proportion to the force and inverse proportion to the mass per Newton's second law. Okay. The elevator problem. Be aware that when an elevator accelerates, it can create a pseudo force on an object inside the elevator. When the elevator is accelerating upwards, that pseudo force seems to strengthen the force of gravity. When the elevator is accelerating downward, the force seems to be in the opposite direction of gravity, so things get lighter. All right. The Atwood machine is a common problem. As long as we have the assumption that the ropes and the pulley wheel are massless and frictionless, then this is simply either an equilibrium problem if the masses are not moving, or a dynamics problem. Typically, the masses are assumed to be moving together. That is, the rope doesn't get any shorter or longer. Each mass is moving along the direction of the rope at the same rate as the other one, so we can treat these as a system. And I'm going to stop there. I'll pick up again with maybe some catch catch up from this section and then talk about friction. Thanks.